Thank you for introduction. And first of all, I'd like to thank the organizers for giving me this very precious chance to talk my recent works. And actually, this is my first time for giving 1 hour long time presentation in this kind of important conference. So I get a little bit nervous, but I'll do my best. So, sorry, is it? Oh. Okay. So at first, I want to introduce my collaborators, Dirk Manske, who is my mentor in the Max Planck Institute, and Yasuhiro Asano, who is my previous supervisor in Hokkaido University, and Yukio Tanaka and Shun Tamura in Nagoya University. And this is content of my talk today. And first, I would like to give you my introduction and my own motivation. And my message of this section is that I want to go beyond proving the existence of edge states. More specifically, I want to see more deeper nature of the topological edge states. And based on this broad motivation, I have done 2 specific works. And the first, I studied the anomalous non-local conductance as a fingerprint of chiral edge state. And in this work, we will propose a smoking gun experiment for detecting the chiral motion of the topological edge states. And in the second part, I will talk about the anomalous proximity effect of Planar topological Josephson junctions. And in this work, I will propose a practical, promising experiment for detecting the anomalous proximity effect, which is one of the most striking phenomena reflecting the presence of the Majorana edge state. And finally, I want to give you a summary of today's talk. So, let me start. So, as you may know, the topological superconductor is characterized by the topological number defined by using the wave function below the superconducting gap. And if the topological number takes non-zero value, in that case, we call it topological superconductor. However, the topological number itself is quite mathematical object, but the physical manifestation of the non-trivial bulk bound topology is the emergence of the gapless boundary state at the material surface, like this. And the relationship between the non-trivial bulk bound topology and the emergence of gapless boundary state is guaranteed by a plane spark called bulk boundary correspondence. And in case with the spin triplet or spinless superconductivity, the topological edge state at zero energy can be described by the Majorana bound state, satisfying this relation. And this relation means particle equals to its own antiparticle. And such kind of exotic excitation can be used for forming the fault-tolerant topological quantum computations. And so due to such kind of reasons, the physics of topological superconductivity have attracted much attention for more than 10 years, more than decades. And in the primary stage of this context, we only focus on the chiral edge states with broken time reversal symmetry. This kind of topological superconducting state is quite similar to the quantum Hall or quantum anomalous Hall state in insulating system in terms of topology, discovered in 1980s. But soon after the discovery of topological insulators, the theory for insulating system is extended to the superconducting system, and then we now know that there is helical type of topological superconductivity characterized by D2 topological invariant. And in this case, we can find a counter-propagating pair of the edge states. And moreover, for the nodal system, we can find the, if the superconducting gap has the node like this, we find some flat band and Dreyfus band states like this. And such kind of flat band, highly degenerate topological states can also characterized by the topological invariant depending on the momentum parallel to the surface we consider. But this is just a representative example for the topological edge states, but nowadays we have know that there is rich variety in the type of topological edge states and its relevant topology. But how we can detect them? It is very important subject in this context because, as I said, the topological superconductor is characterized by the topological number, and topological number itself is quite mathematical object, and only the physical manifestation is the emergence of the topological edge states. So the detection of topological edge states will give the straightforward evidence for the topological superconductivity in principle. So how can we detect them? The most commonly used or most practical or most used method or tool for measuring the topological edge states is the tunneling spectroscopy in the normal metal and superconductor junctions. And when we consider the conventional, non-topological superconductor, in that case, the conductance spectrum shows the gap structure like this, reflecting the presence of superconducting gap in the superconducting segment. But when we replace the conventional superconductor with the topologically non-trivial one, in that case, we will get the zero bias peak structure. And this peak implies that the topological edge state appearing at the junction interface enhances the low energy transport. Actually, the shape of peak or detail, the structure of the peak would be depend on the model or real configuration of the materials and so on. But the emergence of inner gap enhancement of conductance is quite ubiquitous behavior under the presence of the topological edge states. So actually, the tunneling spectroscopy is one of the most powerful two method experiment for identifying the presence of topological edge states. And actually, most of all, experimental evidences for the topological edge states so far are obtained from tunneling spectroscopy. For instance, strontium luthenate is believed to be host the time reversal symmetry broken unconventional superconductivity. And in that case, in close two-dimensional electric structures, and in this case, we can expect the chiral edge states protected by Z topological invariant. And actually, a planar tunneling spectroscopy experiment shows the zero energy peak structure. And also, the copper bismuth selenide is one of the candidate of the topological superconductor. And it is believed to be that this material exhibit the odd parity nematic superconductivity. And in that case, we can expect helical edge states at the material surface. And actually, a soft point contact experiment shows the prominent peak from this material. And YBCO, which is high TC superconductor, can also the topologically non-trivial. High TC superconductor is characterized by the D-wave pairing symmetry, having the gap node on the Fermi surface. And we can have the flat band topological edge states, its material surface. And an experiment demonstrates the zero energy peak structure only when making the junction for the appropriate direction. And not only for the natural compound, we can also find the zero energy peak in some artificial topological superconductors. And the most representative example in this direction is the semiconductor superconductor hybrids. And in this experiment, they use the semiconductor nanowire proximized to the conventional superconductor. And then when we additionally apply the magnetic field to this system, we will get the Majorana bound states at the end of the nanowire section. And actually, the experiment shows the clear zero bias conductance peak, which is quantized. Really nice experiment, shows the evidence for the topological superconductivity. And we can also find the topological edge states in the magnetic atom chains fabricated on the conventional S-wave superconductor like this. And they measures the DADV by using STM techniques. And this blue line denotes the spectrum for when the tip is close to the middle or inner side of the atomic chain. And in that case, we do not find any peak. But if put the STM tip at the end of the magnetic chain, then we find zero energy peak, manifesting the presence of topological edge states. So this result is just a representative example of the experiment evidence, but nowadays we have many signatures from the topological edge states via the tunneling spectroscopy. So by summarizing my talk above, we can say that for the first case, much effort has been devoted to detect the topological edge states. And now we have many experimental evidences for the topological edge states in various systems. So this is just my opinion, but I suppose that now is the time for go beyond proving their existence. But now we can embark on investigating the nature of topological edge states more deeply. And based on this motivation, we have down two specific work. And the first one, we will propose a smoking gun experiment for detecting the chiral motion of the edge states. Not only the presence, I want to see the chiral motion of the edge states. And in the second part, I will talk about the practical experiment for detecting the Majorana bound states. The anomalous proximity effect is one of the more striking phenomena manifesting some profound nature of Majorana bound states, as well as odd frequency Cooper pairs. So let's move on to the specific my works. So as I said, tunneling spectroscopy is a very powerful method for proving the existence of edge states. However, actually, any type of the edge states can cause the inner gap enhancement in the conductance spectrum. So in this sense, the conventional tunneling spectroscopy is, how to say, powerless to capture the nature, individuality of edge states. However, I suppose that to bring the physics of topological superconductivity to the next stage, we have to catch the individuality of edge states from some experiments. So in this work, we focus on the primary example of topological superconductor, that is chiral P-wave superconductor, and propose a smoking gun experiment for identifying chiral nature of the Majorana edge states. And the key idea of this work is that we use the non-local transport in the ferromagnetic grid and chiral P-wave superconductor. And actually, we need ferromagnetic grid to get the finite charge current in this system. But anyway, I will explain how the chiral Majorana edge states affect the non-local transport in this system in what follows. So first, I'd like to explain our model. I just use very simple single band model for describing this junction. For the ferromagnetic grids, we just put the exchange potential here. And the direction is not fixed at present. This is just like parameters. And the superconducting segment is described by the BDC Hamiltonian, given like this. And here we find the pure potential of the chiral P-wave superconductor. And the D vector, which characterizes spin configuration of the spin triplet Cooper pair, is in this case fixed to the around z-axis. And we are interested in the non-local conductance of this system, defined like this. And here, I beta is current in read beta, for instance, in this case, read 2, due to the upright bias voltage to the read alpha, in this case 1, where the read beta and superconductor is both grounded. And within the Bronder Tinkham-Krapp-Weick formalism, the non-local conductance can be calculated by this formula. And here, the first term gives the amplitude of elastic cotunneling. And in this process, electron injected from one reed is reflected as an electron in different lead. And in the second term gives the amplitude of the crust and ray reflection. And in this process, an electron injected from one lead is reflected as a whole in different lead. And the non-local conductance is determined by the competition between these two scattering processes. And in our calculation, we just numerically calculate this amplitude by using lattice Green's function techniques. But in this talk, I do not go into details of this method. But alternatively, I won't talk about our result in what follows. But before showing the result, I want to talk about our expectation, what happens on this system. So let's assume that the chiral energy state moving from lead 1 to lead 2 in this direction, something like this. So when we inject the electron from lead 1, in that case, we can expect that the chiral energy state assist or mediate the non-local transport from the lead 1 to 2, like this. So as a consequence, we can expect the non-local conductance from lead 1 to 2, irrespective of distance between two leads, because the Majorana state itself is just a propagating model, so they don't feel any restriction from superconducting coherent lengths and so on. So the non-local conductance from lead 1 to 2 may become very insensitive to the distance between two leads. On the other hand, when we inject the electron from lead 2, in that case, the created Majorana moving like this and absorbing to the ideal electrode attached to the superconductor. So in this case, the chiral Majorana never assists the non-local transport from lead 2 to 1. So as a consequence, we may find G12 non-local conductance from lead 2 to 1, it goes to almost 0. So we can see some drastic contrast between G21 and G12, reflecting the motion of the chiral edge states. And this is our expectation. And then I will show you the numerical result. And I can say that our expectation is completely correct. Agree with our expectation, our numerical calculations. So this figure, so for calculating this figure, we consider the anti-parallel magnetization on the axis, and the exchange potential, magnetic moment dependence will be discussed later. But now we just consider the anti-parallel one along the axis. And this figure shows the non-local conductance from lead 1 to 2 as a function of bias voltage and distance between two leads. And we find that the non-local conductance for low bias voltage becomes finite, irrespective of distance between two leads. On the other hand, this is a result for the non-local conductance from lead 2 to 1, and in that case, we find the non-local conductance is almost 0, irrespective of distance between two leads. So we can indeed find the drastic contrast in the two types of conductance spectrum, non-local conductance spectrum, reflecting the chiral motion of the edge states. And now I want to talk about the advantages of our proposal. First, as I said, this kind of distinct drastic contrast must be the unique in the presence of chiral edge states. And the second, which is more importantly, in the second, we can identify the chiral edge states only from the qualitative information. I mean, we don't need any quantitative information like quantization and so on. Yeah, actually, the perturbation or something will modify the spectrum, detailed structure of conductance spectrum. But if we can find something finite and zero contrast, then we can conclude that there is chiral edge states. So in this sense, we believe that this is very promising and powerful strategy for identifying the presence of chiral Majorana edge states. And then I want to talk about the detail of our result. And specifically, I mean, I want to study the exchange magnetic moment dependence of the non-local conductance. And first, I focus on the amplitude of exchange potential in the ferromagnetic grid. And this figure shows the non-local conductance from read 1 to 2 as a function of amplitude of the exchange potential along the axis. So in this figure, I just consider the parallel or antiparallel magnetization. And if there is no magnetic moment, I mean, if there is only we use the simple normal method, in that case, the non-local conductance goes to 0, which implies that elastic cotoneering and cross and wave reflection have the same amplitude. And then if we consider the antiparallel magnetization, in that case, the non-local conductance goes to positive finite, which means the cross and wave reflection becomes dominant. And if we consider the half metallic limit, I mean, one of the spin band is completely pinches off from the film level due to the extremely strong exchange potential. In that case, the non-local conductance is quantized to the sharpening conductance. But we have also checked that this kind of quantization is not so robust. I mean, if we put the strong impurities or strong potential barriers at the junction interface, in that case, the non-local conductance decreases from the quantized value. So this quantization is not protected by topology, something like quantum Hall or something like that. And then when we consider the parallel magnetization, in that case, the non-local conductance goes to the negative finite, which means elastic cotoneering is dominant. And so the next slide, I want to explain why this kind of result can be obtained. So when the D vector is parallel or antiparallel around the exchange potential magnetic moment, in that case, elastic cotoneering processes occurs between the electrons having same spins. On the other hand, the cross and wave reflection occurs between electron and hole having opposite spins. So with the parallel magnetization, equal spin scattering process never disturbed, whereas the spin flip in the cross and wave reflection disturbed. As a consequence, elastic cotoneering becomes dominant, and then non-local conductance goes to negative finite. But when we prepare the antiparallel magnetization, in that case, elastic cotoneering is disturbed, whereas the spin flipping in the cross and wave reflection never disturbed. As a consequence, we get cross and wave reflection dominant case, and then non-local conductance goes to positive finite. So now we can get some physical description for the previous figure. And next, I want to talk about the direction dependence of the non-local conductance. And this figure shows the non-local conductance with various magnetic moment alignment. But the important point is just important message from this figure is just simple. First, the maximum amplitude magnitude of the non-local conductance is obtained when the exchange potential is the parallel or antiparallel to the D vector. But more importantly, the non-local conductance goes to 0 only when the exchange potential is perpendicular to the D vector. So in this sense, so the main message from this figure is that we can find distinct contrast between G12 and G21 with the broad range of the magnetization alignment. I mean, G12 is, of course, G12, which is non-local conductance from read 2 to 1 is always 0, respective of exchange potential details. So we can find drastic contrast in broad range of magnetization alignments. And so this means that in real experiment, the D vector may be more complicated or tilted from the ideal direction or exchange potential also, but we can still find distinct contrast between two kind of non-local conductance spectrum. And finally, we examine the wave function of this system. more specifically, we focus on the eigenstates, eigenwave function of this system having the largest contribution to the crossed and wave reflection. So we pick up the eigenstates contributing this kind of scattering processes. And this is a numerical result. And this is the amplitude for electron component of the wave function. And this is the result for the Hall component of the wave function. And we find significant amplitude of electron component in the read 1, and we find Hall component in read 2. But more important point is that the electron wave in read 1 and the Hall wave in read 2 is actually connected by edge states, having the electron and Hall component with same amplitudes. So we have confirmed that the unusually long-ranged non-local transport in this system is indeed mediated by the chiral Majorana edge states. So let me summarize the first section of my talk. So to propose a smoking gun experiment for identifying the chiral Majorana edge states, we have studied the non-local transport in the ferromagnet and chiral P-wave superconductor hybrid system. And we have found that there is some drastic, distinct contrast between the two kinds of conductance spectrum reflecting the chiral motion of the Majorana edge states. And we can measure the both of two spectrum by replacing the read wire with which the bias voltage is applied. So we can measure both of them in a single experiment setup. And moreover, we can identify the chiral Majorana edge states conclusively only from the finite zero contrast. So I suppose that this strategy is very powerful, promising for getting the smoking gun evidence of the chiral Majorana edge states. And this work is summarized in this paper. So if you have interested in, so please check it. And let's move on to the second topic. And in the second topic, I will discuss about a practical experiment for detecting the anomalous proximity effect. And anomalous proximity effect is one of most striking phenomena, reflecting the profound nature of Majorana bound states, as well as odd frequency Cooper pairs. So before going to the details of our proposal, I want to briefly review what is the anomalous proximity effect. And so first, I want to talk about the conventional, usual proximity effect. So let me consider the normal metal and the superconductor junction. And if we make this kind of with conventional S-wave pairing symmetry, and in this case, the Cooper pairs can penetrate into the attached dirty normal metal, and then they form the gap structure in the local density of states of the normal metal. And we can also find the reduction in the electric resistance, and also we can find the magnetism. So in this sense, due to the penetration of the Cooper pairs, the attached normal metal obtained superconductivity like electromagnetic properties. And this is usual proximity effect. But when we replace the S-wave superconductor to the P-wave superconductor, spin triplet P-wave superconductor, in that case, the local density of state of attached dirty normal metal shows the zero energy peak structure, alternatively to the gap structure like this. And we can also the zero bias conductance peak or more rich Barres anomalies in low energy transport in this junction, and we can also the paramagnetism instead of diamagnetism. So this kind of the counterintuitive or anomalous, very anomalous proximity effect is called as the anomalous proximity effect. And to understand why anomalous proximity effect occurs, we have to employ the Majorana bound states and odd frequency Cooper pairs. So in what follows, I want to explain how the Majorana bound state and odd frequency Cooper pairs are related to this unusual phenomena. So the first, I focus on the Majorana bound state. So as I said, P-wave superconductor can host the Majorana bound state at its surface or junction interface. And when we attach the dirty normal metal, not only Cooper pairs, but also the Majorana bound states can penetrate into the attached dirty normal metal. And as a consequence, the penetrated Majorana bound states can form the zero energy peak structure in the local density of states of attached dirty normal metal. And moreover, it has been proven that such kind of penetrated Majorana bound states can cause the resonant transmission in this junction. As a consequence, we can see various anomalies in the low energy transport. So by employing the Majorana bound states, we can explain the nature of several aspects of the anomalous proximity effect. We can explain by the Majorana bound states. And then I want to talk about how odd frequency Cooper pairs related to the anomalous proximity effect. And before that, I want briefly review the restriction for the pairing symmetry. The pairing symmetry is characterized by the anomalous part of the Green's function, F, and it contains two spin degree of freedom, two spatial coordinate, and frequency, reflecting the two electrons forming Cooper pairs. And due to the Fermi-Dirac statistics, it must satisfy this relation. It means we need minus sign with replacing two electrons. And in some cases, spin brings the minus sign, or in some cases, parity brings minus sign or frequency and so on, but totally we need minus sign. And if we see the isolating or bulk P-wave superconductor, we find spin triplet P-wave superconductivity pairing symmetry. So it means the even in the spin replacing or and odd in the parity, orbital exchanging. And so to satisfy this relation, we finally need even frequency. But however, when we put the dirty normal metal, the penetrated Cooper pair must have odd frequency. This is because that, the spin component is still triplet, but the orbital part must be changed to the S wave because the dirty normal metal, in the dirty normal metal, only the isotropic pairing can remain. So to satisfy this relation, finally, we need odd frequency. So in short, so in the attached dirty normal metal, we have S-wave triplet odd frequency Cooper pairs. And it has been also demonstrated that the odd frequency Cooper pairs can cause the paramagnetic Meissner effect, paramagnetic response. So the unusual magnetic response of the anomalous proximity effect is explained by employing the odd frequency Cooper pairs. And by summarizing above explanation, the anomalous proximity effect is one of unusual, striking phenomena manifesting the nature of the Majorana bound states and odd frequency Cooper pairs. And both of them is one of novel and important concept in recent physics of superconductivity. So I suppose that the anomalous proximity effect is really, really important phenomena for investigating deep nature of topological superconductivity. But so far, no experiment have demonstrate this conclusive evidences for this effect. And this is because that there is no suitable superconducting systems for fabricating the dirty normal metal and topological superconductor junction with hosting the Majorana bound states. But now we have found one promising topological superconducting system for observing the anomalous proximity effect. And that is Planar topological Josephson junction. And this system is theoretically predicted very recently, 2017. And in this system, they use the thin film semiconductor with two conventional superconductor fabricating the Josephson junction. And by applying the magnetic field, we will get the Majorana bound states topologically protected. The greatest advantage of this proposal is that they uses thin film semiconductor whose fabrication techniques are very well established. So actually, soon after the theoretical prediction, the several experiments have already demonstrated or confirmed the realization of planar topological Josephson junction. For instance, this figure is picked up from this paper, but anyway, they form the Josephson junction with the square geometry and put the gold contact to the junction region here. And then they measure the DIDV, differential conductance of this system. And they find that there is a prominent zero-bias conductance peak only in the topologically non-trivial phase. So to observe the anomalous proximity effect, what we need is just what we additionally need is just a disordered segment between the junction, planar topological junction, and contact. I mean, if we can insert the dirty number segment between the contact and junction, like here, in that case, we can see the anomalous proximity effect. We are not experimentalists, so maybe we need to do the experiment. Maybe we need more detailed techniques to realizing this junction, but we suppose that it is possible. For instance, if we prepare, so for instance, at first we prepare the T-shaped 2DEX, and then put the 2S wave superconductors like previous experiment, and then, for instance, by using FIB techniques to make extended normal segment dirty, and finally, we can get some superconductor hybrid systems for observing the anomalous proximity effect. Actually, this effect is very promising for detecting the anomalous proximity effect because the Majorana bound state is directly interfacing to the dirty normal metal. But no one has to be studied the anomalous proximity effect in this kind of tricky junction. I mean, we don't use pure P-wave superconductor in this case, and instead of it, we use some planar topological Josephson junction. So in this work, we will confirm that the planar topological Josephson junction can indeed cause the anomalous proximity effect. So let me explain our model. So we use the BD to describe the topological Josephson junction. We use this kind of BDZ Hamiltonian, but it's quite complicated. So I just want to talk about the essence of this Hamiltonian. At first, we can find the Rashba spin-orbit coupling term, which is naturally induced in the two-dimensional electron gas like thin film semiconductor. And we also find the Zeeman potential induced by the imprime magnetic field in this direction. And we can also find two pair potential terms constructing the Josephson junction. And then the dirty normal metal segment is described by this Hamiltonian. Normal part is almost the same, but we also find the random on-site potential instead of pair potential to describe the disorder in this segment. And the reed wire is described by this simple Hamiltonian. In this case, we suppose that there is no spin-orbit coupling, but there is still Zeeman potential. And we also assume that the bad transpassy between the reed wire and the dirty normal metal, which is a relevant condition for the experiments. And to this kind of bad interface, I just use small hopping integral between the reed wire and dirty normal metal. And under this circumstance, we can use the BTK formula for calculating the differential conductance of this system. And we numerically calculate the Andreev reflection probability and normal reflection probability by using lattice-Green's function techniques. So before talking about our numerical result, I want to briefly review the topological property of the planar topological Josephson junction. But actually, this is not our investigation. We just follow this previous paper So I want to just talk about the result. So the planar topological Josephson junction can be characterized by this kind of Z2 topological invariant. And here we find the winding number defined like this. And when the winding number becomes odd integer numbers, then this number becomes non-trivial. So as a consequence, with the odd winding number, we can find robust Majorana bound states at the end of junction region of planar topological Josephson junction. And this is the result for the planar topological winding number as a function of the phase difference and the applied Zeeman potential. And we can find that there is that odd winding number. I mean, topologically non-trivial phase can be found in the broad range of this the parameter, except for this white or brown region. So we can find a significant topologically non-trivial phase. And actually, the details of the topological phase diagram can be depend on the parameters, but actually we can find the topological non-trivial phase with the broad range of parameters or very insensitive to the parameters. And next, I want to talk about differential conductance in this system. And this figure shows the zero bias conductance as a function of phase difference and Zeeman potential. And we soon find that the non-local conductance quantize to twice Kelvin conductance only in the topologically non-trivial phase. So if we compare, we can soon find it. Non-local conductance is conductance, zero bias conductance is quantized only in the topological phase. And now I want to emphasize that this is the non-local conductance for the with the dirty normal metal. I mean, there is no direct contact to the Majorana bound states, but we can find zero bias conductance quantization irrespective of strength of potential disorders in the disordered dirty normal metal segment. So this is different from a usual conductance quantization. And this figure shows the differential conductance as a function of bias voltage, and this is for topologically non-trivial phase, and this is for topologically trivial phase, non-topological phase. And for the topological phase, we find steep zero bias peak structure, whereas the spectrum for the non-topological phase shows the gapped structure. But actually, we can find some enhancement in the gapped region, which might come from the Andreev bound states formed in the planar topological junction, Josephson junction. But anyway, this conductance spectrum shape changes drastically across the topological phase transition, and which is useful for detecting in the experiment. And then I want to talk about the local density of state in attached dirty normal metal. And this figure shows the density of states, local density of states in the dirty normal segment at zero energy. And we soon find that the local density of states has a significant amplitude only in the topological phase. And this figure shows the local density of states as a function of energy and position within the dirty normal segment. Position means the distance from the read wire dirty normal segment interface. And we can soon find that zero energy peak appears entire the dirty normal segment. So this result implies that the Majorana bound states originally located at the end of planar topological Josephson junction penetrates into the attached dirty normal metal. So we have confirmed an important aspect of the anomalous proximity effect in the planar topological Josephson junction. And then I want to talk about the pair amplitude of auto-frequency Cooper pairs defined by this mathematics. And we soon find that the auto-frequency Cooper pair has this significant amplitude only in the topologically non-trivial phase. And we can also find significant amplitude of auto-frequency Kuiper pairs in entire the dirty normal method segment. So we have confirmed the penetration of the auto-frequency Kuiper pairs in our proposed system. So finally, I want to summarize our results for the second part. Yeah, we have demonstrated the anomalous proximity effect in the Planar Topological Josephson junction, and we have confirmed it indeed occurs. So this system is fabricated on the semiconductor thin film, whose fabrication techniques is very well established. And moreover, the Planar Topological Josephson junction itself has been already demonstrated in the experiments. So we believe that our proposed experiment is very practical and promising for achieving the first experimental observation of the anomalous proximity effect, which is one of more striking phenomena reflecting the profound nature of the Majorana band state and odd frequency Kuiper pairs. So finally, I want to give you a total summary of my talk. My broad motivation for this work is that I want to go beyond proving the existence of the edge states. More specifically, I want to see more profound natures of the topological edge states. And on the basis of this motivation, at first, we have studied the anomalous non-local conductance as a fingerprint of chiral edge states. And in our calculation, we just think the simplest chiral P-wave superconductor. But by developing our theory or generalizing straightforwardly, we can use our strategy to see the chiral edge states in the uranium telluride. Yeah, uranium telluride is nowadays believed to be exhibit chiral P-wave superconductivity, but it's non-unitary, but chiral P-wave superconductivity. So we can use our strategy for test or demonstrate, prove the chiral edge states in this material. And in the second part, we have checked the anomalous proximity effect in the Planar Topological Josephson junction system. And as I said, this system is fabricated on the semiconductor thin film, whose fabrication techniques are very well established. So we believe that our proposed experiment is very promising for the first experimental observation of this effect. So thank you for your attention.